To the first installment of the 2022 Berkeley Seminar Series here at Topos Institute. So in this informal seminar series, we're going to highlight the work being done here as well as ideas and perspectives from our friends in the area. And so to start things off, we have our very own Valeria de Paiva, who will tell us about natural language inference for humans and machines.
Thank you. In my books, we applaud at the end, if you like it. And if you don't like it, we throw a piece of paper. But thanks, Evan. Thank you, everyone, for being here. And yes, it's very nice to be restarting the Berkeley seminar, because we all kind of missing seeing each other and talking to each other. And as Evan was mentioning, I wanted to talk about some work that I do. So I have been, from last year, trying to tell you guys about all the different areas that I work with. And so I started talking about dialectical categories, which is what I did my thesis on, and it's my more mathematical work. Then, more recently, I talked to you guys about constructive modal logics. And today, I'm being very, logics in the plural. And today I'm being very ambitious, because I want to talk to you about my work on natural language semantics and natural language understanding and NLP, natural language processing. So, and it's very ambitious because I want to talk about two somewhat unrelated strands of work, but you'll see that in a little while. So let's get going. It's always good to start by talking a little bit about personal stories, and I think one of the personal stories that I think is very important is this idea that mathematicians, by and large, are told over and over again that natural language is ambiguous, messy, and imprecise, and that one should study artificial languages instead. And some of us beg to differ from this opinion. Some of us think that actually that's what makes natural language such a challenging and interesting subject. And amongst the people who kind of do that and have done that, kind of started this trend is Richard Montague, who is a famous American logician, murdered in 74 or 72 near Los Angeles. This is my friend Ann Copestake, who is at the moment the head of the Cambridge Computer Laboratory, and with whom I wrote my first, my first book is with her on stuff to do with machine dictionaries. And that was an old project that we both worked on called Aquilex for lexical acquisition. And that's Mary Dalrymple, who somehow is responsible for me being here and having been in Silicon Valley for the last 22 years. Because Mary was the person who kind of came up with this idea that linear logic was very important for natural language semantics. I'm not going to talk so much about that because, life has this menu of changing under our feet, and things nowadays are very, very different. So I wanted to introduce from the beginning the other side of this coin of natural language understanding, kind of contrasting Montague with Chris Manning, who kind of in 2015 already was talking about the tsunami of deep learning in computational linguistics. And I'm going to use computational linguistics and formal semantics and NLU, natural language understanding, as synonyms, use whichever I prefer at the moment. But if you disagree very strongly, you can say so, and I'll try to keep them separate. But I think they are mostly the same. And so in 2015, Chris is a, I mean, I'm not going to mention all the things that he is, but he is kind of one of the professors in Stanford who is a linguist and also a professor in computer science. And he has, for people who are in this business, he has more than 100,000 citations to his work. So he's in a class of his own as a researcher. And he was, in 2015, he stopped being the president of the ACL, which is the Association for Computational Linguistics, and he has this very short and very prescient sort of discussion of the field in 2015, when he was saying that he had been told that NLP is like a rabbit in the headlights of deep learning machine waiting to be flattened. And I think lots of us have the same feeling that, you know, the tsunami, the wave is coming and it's kind of battering us over and over again. But some of the other things that he mentioned in this very short and very, it aged very well, this thing, because, you know, 2015 is now 7 years. So, you know, it's still worth it's worth reading, and on the other hand, it is kind of surprising how people keep making predictions that eventually don't get there. So Jeff Hinton, who is another, I mean, there are the three big guys of deep learning: Jeff Hinton, Yann LeCun, and the guy from Facebook. You know, that's Yann LeCun. So Jeff Hinton said something like, "I will be disappointed if in 5 years' time we do not have something that can watch a YouTube video and tell a story about what happened." And that's still not the case. And actually, we keep finding that things that we thought deep learning could do, it couldn't. On the other hand, you get things like the hype carries on being every time more interesting, with different variations on the wonderful things that deep learning can do. So I want to tell a story that actually kind of tries to put together some of the work that I was mentioning in the previous slide with the work that both Chris and Henry Schutz have been doing on deep learning, but not deep learning as a subfield of machine learning, but actually as a subfield of computational linguistics, so kind of trying to take in consideration the linguistic insights. So, you know, I kind of wanted to mention that this is another very nice video to watch, which is, again, this a bit more modern, still Chris Manning talking to Susan DeMere, or I don't know how to pronounce her surname properly, but she's a fellow of Microsoft, and they were trying to describe all the good things that we get from deep learning and all the things that we are still missing from deep learning. So I'm kind of getting to the end of the personal stories, but, you know, this is kind of my professional life in the Valley. So I came to work in Xerox PARC, and I stayed there for almost 9 years. Then I went to Cool, which was a search engine created by some guys who left Google, so kind of and which kind of burned in 2 years. Then I went to work for a horrible place called Reason Commerce that, thank goodness, doesn't exist anymore, so I can say things like that. Then I went to work for Nuance in 2012. Then I went to work for Samsung in 2019. And now I'm here kind of doing what I actually like to do, which is thinking about hard problems using mathematical tools. And one of the things that I kind of, the thing that I started in PARC to do was what we got to the things, when we got the systems working there, and there was a huge effort that had started many years before I arrived. We kind of got a system that we called Bridge. And it was called Bridge because it took words, sentences in English, and transformed them into logic, and then did some inference with this logic. So you could, in particular, it did question answering, because again, there was some money from the government, in this case, I think, ARPA, which kind of paid for this project called what is the name of the project? I mean, there were lots of different projects in PARC, one after the other, and but the bridge thing was exactly about trying to answer questions that were much more complicated than a question that I have here. So here I have this thing about the crow slept and the bird slept, and you're supposed to know that the bird slept kind of follows from the crow slept. It's an easy entailment, and if I had the crow slept and the crow didn't sleep, you'd have a contradiction. And if I had the crow slept and the bear slept, you'd have a neutral situation, because it's consistent as a bit of logic, but it doesn't follow from the bear, has nothing to do with the crow. So this project that I'm trying to remember the name now, which was a very big project with partners from Europe, Israel, and lots of places in the US, it was about reading the newspaper and concluding things from the newspaper. So you have this question answering, where the passage then was very complicated, was a piece from a news story, and the question was a very short thing that you wanted to know if it followed or not from the big passage. And when I actually left PARC, so we had lots of papers and stuff about the system bridge. I'll talk a little bit more about it later, but when I left PARC to work for this search engine in 2008, I had a big shock, because of course, when you work for companies, all the work that you do stays with the company. You can't take it with you. And I couldn't even and there was lots of things that had been left in the state of the middle. You hadn't finished. We hadn't kind of got to the end of what we wanted to do. And I couldn't then work on it anymore. I eventually kind of got a research license from PARC and stuff like that, but it was a total disaster. So at that stage, I gave a talk at SRI. I guess you guys know what SRI is. The Stanford, it used to be called the Stanford Research Institute, but nowadays it's a research lab that's been there for more than 40 years, I think. So I gave a talk there proposing to redo everything that we had done at PARC, but all open source. And I think people kind of thought I was a little bit crazy, and I think I thought I was a little bit crazy too, but I'm very pleased to report that almost all of what we had in the bridge system is now available open source for anyone to look at and download and redo it in GitHub. And most of this work was redone by Katerina Kaluli, who was my intern at Nuance, and then she became a PhD student at Constance, and now she's faculty at Munich. And so that's the kind of work that I want to talk to you about today. But so first, I think I don't know how much of the example that I gave about the crow and the bird kind of was clear to you. Of course, the situation in real life is much harder than that one. So these are examples taken from the famous huge corpora of inference done by the guys at Stanford, the PhD thesis of Sam Bowman, who is now in New York. And so they have, when we're doing this in PARC, we had 6,000 pairs of questions and answers and stuff like that. And some managed to get 570,000 pairs. So it's a huge amount of stuff. And here's some examples, right? So you say something like, A man inspects the uniform of a figure in some East Asian country. The man is sleeping. Well, contradiction, right? The man cannot be sleeping and inspecting something at the same time. A soccer game with multiple males playing. Some men are playing a sport. Yeah, entailment and stuff. And you can see that we have several people judging this. This is several different Turks kind of giving their suggestions. So, for instance, on this one here, we have a smiling costumed woman is holding an umbrella, and three of the Turks thought that that is neutral with respect to a woman, a happy woman in a fairy costume holding an umbrella. One thought was an entailment, and the other one thought was a contradiction. So it's this kind of hard problem of what people think is logical inference, what is an entailment, what is a contradiction, and what's a neutrality that we want to deal with. And we want to do it automatically, and you want to do it for systems that are of the order of 500,000 pairs. So the old bridges, the bridges done in Parc, we had, as I was saying before, lots and lots of papers. I think the one that's kind of easier to read is this one, Parc's Bridge and Question Answering System, but from 2007. And my job in this huge collection of people was to be the logician. So this last two here are my contribution to that. And this one is mine attempted saying, well, we need to do this again, because you can't have all this technology that took 40 years of more than a dozen researchers disappearing in Parc. Because the whole group of natural language understanding there was closed down, and now they are restarting a new group. But for a while, all this work had died completely. And so the new bridges, and I finally got there, the new bridges are the ones that we've been doing, and that's why Kaluli is all over the place, because it's mostly her work redoing that. And I want to talk to you about this particular paper, which is about bridging the gap between symbolic, structural, and distributional meaning representations. So the symbolic and structural are the ones that we're discussing before, the ones coming from Montague, and the distributional meanings are the ones in terms of deep learning, and the ones that Chris and Hirish kind of are mostly famous for. So before going into the system themselves, which I'm going to do in a minute, I wanted to show you what was considered around 2007 the main ideas about a division of semantic labor. So I think most people at that stage thought that distributional features are very good for lexical aspects. Semantic similarity is what deep learning is good for. Hypernym and antonym relations, perhaps. Whereas kind of the structural features are the ones that talk about Boolean functions and contextual phenomena. Things like modals, quantifiers, implicatives, hypotheticals. All these things tend to be more structural, and by and large, the deep learning systems have a difficulty with them. There is kind of a collection of works that show the difficulty that they have understanding and learning the so-called structural features.
What's the lexical aspect?
Lexical, it's about the dictionary. So it's this, one of the good things about having these two sides of it is the fact that the structural side of semantics doesn't know very much about about the different meanings of the words themselves. So there is a famous joke about the fact that semanticists used to say that the meaning of life is life prime. So you just translate life into life again, because you just kind of say, oh, go and look in the dictionary. I don't know about that. This is completely opaque to me. Whereas, so this is the stuff where the distributional and the vectors actually are very good, because they do know the difference between a zebra and a horse and stuff like that. They pay attention to this lexical or dictionary side of the semantics. And please carry on asking questions, because that's the point of it, right? And of course, and this is kind of completely without thinking about anything that we're talking about. There's always three approaches, broad approaches to combining a system that's distributional with a system that's symbolic, right? You can add the symbolic features into the distributional features. You can add the opposite. You can inject the distributional features into the symbolic representations. And you can combine the two in some sort of final representation that I'm not telling you exactly how the combination happens. So, in one case, you're putting making the fundamental semantical system the distributional representations or the symbolic representations, or you kind of say, oh, I don't know which one is the most fundamental. So I kind of try to combine the two in the best possible way. So what will happen here is that I wanted to show you our version of number 3, and you can road test it. This is just a demo, but kind of it's in the same directory where the code is. And as Murphy Law would have it, and Katarina is 9 hours ahead of us. So last night when I was preparing the slides, I kind of noticed that the system was down. So I sent her a message saying, what's going on? The system was out, the three demos are down. And this morning she, oh, okay, no, I just needed to reboot. So it's all working at the moment. We can do it at the end. So what sort of symbolic representation I will have? This is a big issue, because linguists kind of vaguely agreed quite a bit on what is the syntax of sentences. And nowadays we have this beautiful, gigantic project by Manning and Joachim Nivre and Dan Zeman and a collection of other guys, which is called Universal Dependencies, which actually kind of has syntax for more than 100 languages. So it's a very important new development, and it's happened after 2000, happened in 2014 or forward. So it's kind of still happening, and it's really very big. But meanings are very different. No two people agree on the meanings, on how one should think of meanings of things. So each researcher that I know kind of comes and presents their own system of meanings, and I'm doing the same. I'm showing you what is my system of meanings, but I'm going to say that actually builds on 40 years of the research that happened at PARC. And so it borrows from LFG, which is lexical-functional grammar, a very important grammatical framework that is also the basis of universal dependencies. And it borrows from the bridge idea, the logic that bridge kind of paid attention to, which has some concepts which are much older than the work in PARC. But has this notion of context that are that is something that we did in this group, this big group in PARC, and we did it because following again John McCarthy's sort of suggestions on how to do AI, how to do knowledge representation, and what we will have here, which is different, so these things are old from the parse system. And here it starts as being very different, because what we're going to do here is we're going to have distinct layers and subgraphs of sentence information along several different dimensions. And this strict separation but controlled interaction between the conceptual and predicate argument layer and the contextual or Boolean layer is what will make this system, in my opinion, a better system. And at the moment, these things are produced by this open source semantic parser written in Java, and it's particularly suitable for the task of natural language inference because it was created exactly with this idea that deciding on what is the best logical representation is very hard because you don't have criteria for what is best and what's worse, what is kind of the best you can say is that I like it more. You don't have ways of measuring. Whereas you do have ways of measuring the NLI, right? You do have ways of measuring whether a sentence follows from the other or not, because you can ask people. You can get them to tell you if that is a valid inference or not. So I think this was a big breaking with the model, or a good advancement when people said, well, yes, we can measure. We can measure because you can ask people if the inference is true or not. So let's have a quick look at I really have to be fast about this, but let's have a look at some of the issues that happen when you do this layering of graphs. So I kind of wanted to use a sentence that shows some of the problems. So the sentence here is, John might prevent the fight. And John prevented the fight is hard enough, because if you're just a mathematician thinking very much in terms of first order logic, you tend to think something like, oh, there was a John, oh, there was a fight, and John prevented the fight. But this is stupid, right? Because if John prevented the fight doesn't exist. So you need to deal with this idea that some of the things that we discuss do not exist. And some people have tried to do that in AI by considering notions of existence and stuff like that. But it's a mess. It doesn't get the results that you want it to get. So we reckon that this idea of having different contexts does kind of deal with these issues of partial existence and stuff like that much better. And so we start like everyone else used to do, kind of before deep learning. Everyone started with a full syntactic parse of the sentence, and we used to use Stanford Core NLP. Nowadays we use Space, because space is faster, and speed is of essence here. And then we use something that is not as good as I wanted to, because we use Stanford enhanced universal dependencies. And universal dependencies exist for 100 languages, but the enhanced dependencies don't exist for all this language. They only exist at the moment for English, and there's 3 or 4 kind of on the way, but they don't exist yet. And what we use by and large here is rewriting. We rewrite what used to be the Stanford Core NLP into our own dependence graph. And then we have this notion of concepts. This is the central graph of this representation, which you call JKR for graphical knowledge representation. Not a very clever name. I wish I had thought of something better, but especially because being Brazilian, I sometimes get very confused between JKR and GKR. So, if I missay it, it's the one with the G, not the J. And when we kind of talk about the concepts, we talk about what is talked about in the sentence. So you talk about the propositional content of the sentence. The nodes and this is very important, the nodes represent concepts and not individuals. And you might say, as a mathematician, you might say, I don't care about that, who cares about concepts or individuals? But most of the model theory that we do is with individuals, and we actually need the notion of concepts instead of the individuals for some of this business of considering the things that don't actually exist. And that's what I was saying is about the claims about existence of the concepts described by these content words will be dealt with by this other notion of context. But the concepts kind of have to be able to deal with this logical notion of context. And that means that we have no claims about the existence of the instances of these concepts. We only have claims about the existence of the concepts themselves. Then we have a graph that I never looked at, the grammatical properties, but you have to have it. And it actually kind of gives you lots of information for the more semantic bit. That's what we wanted to do. You have a lexical subgraph, which, as I was saying, is a way of kind of mapping from the sentence into some sort of notion more in the world. So we kind of, we map the words of the sentence into concepts that are at the moment into WordNet, and from WordNet you can map into an ontology that's called Sumo, and this is a way of grounding what the sentence is talking about. If it's not making sense, please ask. It's a little bit complicated in ways, right? Because, remember that as much as we're doing logic and category theory, when you do semantics, what do? You do a function from whatever you're trying to explain into something that's in the world. So what we are saying here is that you understand a sentence of English by mapping it into something that is a dictionary of English plus a conceptualization of this dictionary in terms of relationships between the concepts, which is given by this Sumo ontology. Yes, David?
Would it be sensible to study a graph where the nodes were words and the edges were, when one came after the other in a sentence, you increase the weight? You take a corpus and you kind of look at, like you make a graph where it's kind of short words or long edges, or maybe I prefer short edges when there are many sentences that put word A before.
Right. No, that's completely different, right? This is what we're talking about now is exactly the statistical view of this stuff. That is the other half of the story that will come in a minute. But no, here what we're talking about is more the logical way of thinking about that, doing model theory of the collection of sentences.
Is there enough structure on the logical, the semantic side, or the syntactic side to call it really model theory?
Yeah, kind of.
I mean, just this map from your lexical structure to from your sentence graph to the concept graph. Is there any structure at all?
Well, there's several different kinds of structure there, Brandon. Kind of, there is this. You see, the graph that you get on the semantic side of the stuff it can be thinking of that as a sentence in first order logic. So it does have, it will map into something that looks like there is a predicate prevent, and there's an individual John, and there was a map that took fights to some specific fights that we're discussing here, and that was this one that John prevented. So the thing on this side of on this side, whenever you're doing model theory, you have this is the stuff that we are trying to explain, and this is the explanation, right? And a functor, like usual. So on this side, there is always enough structure, and people like the old AI guys used to do it with first order logic plus extra notions. And people, more modern people nowadays, are doing it with type theory instead of first order. But none of these things deals with this issue that I'm trying to tell you about here, which is this business that you have this notion of intentionality of what is happening that I think is better captured by this notion of context that you haven't seen yet, but that's the next bit of the structure. So the thing that I tried to talk to you guys when I last talked about constructive modal logics was this idea that that we are told as mathematicians that it's good enough to do classical logic or intuitionistic logic, and that modality. I mean, remember I started my talk on constructive modal logics with a famous quote from Russell saying that modality doesn't make sense and stuff like that. But it's very clear that that's because he believed on his own advice about not thinking about natural language, because natural language does require completely dealing with modal notions and so-called intentional notions. And I have proof of that. I had some interns many years ago in Park, and we kind of looked at text that was completely technical text, no poetry, no unicorns, no wanting things. It was just about kind of fixing photocopier machines. And we discovered that, yeah, you know, when one does whatever, I mean, we are paid by the guy, so we did photocopy machines, and there was a kind of discussions between different technicians saying, well, if the cable is broken, just cut this other bit of the lid and kind of put a bit of sellotape there, and we'll work and wait until the new part arrives and stuff like that. And when we actually analyze what was happening, I think I now have to kind of think hard what was the number, but there was something more, around 60% of the sentences had some notion of intentionality or modality into them. So, you know, and I expect it to be something like 3% or something like that, because, you know, we normally associate intentionality with these things like metaphors and paraphrases and stuff like that. But
Can you give examples of what?
well, there's one that I just gave. You might think that that's a completely extensional sentence, right? If you sorry, the sentence, this one I have repeated so many times that I have to be able to repeat it completely. If the cover is rigid, cut the cable to make it more flexible. And the more flexible is totally intentional. You have to kind of compare it to some other flexibility that were there. And you know, if you don't have that notion, then you don't understand the meaning of the sentence as said by the guy. You know, think about it, and we can discuss it later. In any case, the point on the sentence "John might prevent the fight" is that we will have this context where the fight that didn't happen existed. So we will have this notion of contexts that are there's contexts that are veridical, things that really happen. There's contexts that are anti-veridical, things that did not happen. If I had said John didn't sleep, then I have an anti-veridical thing about a sleeping event of John. And there's things that are averidical, like if I say John believed in that he had prevented the fight. We don't know whether he did or not. He believed that he did. But, you know, Mary, who was in the same scene, might say, no, nothing to do with him. Well, the guys kind of got tired. So the point is that this separation between context and embedded context and concepts is what the logic that we had at Park was good at. And it deals with things like implicatives and factives, which I don't expect you guys to know anything about, but are kind of things like phrases like John managed to open the window. When you hear a sentence like John managed to open the window, you are supposed to conclude that that the window was opened, because if he did manage to do it, then it means that he actually, that there was some difficulty, and that's the hard bit, the bit that linguists tend to think about. But for us mathematicians, what you want to know is that the window was open, or closed, sorry, whatever. And these are the implicatives and factives, and imperatives and questions and conditions, and lots of interesting stuff that linguists enjoy playing with. And these things can be done using graphs, and they can be done using some of the ideas of semantic web, kind of using triples of this traditional sort. And our proposal is to say that actually we can separate the symbolic or structural features of reasoning with language versus the distributional ones using those kinds of graphs. And you kind of say, well, when you want to put it all together? And I say, no, not really. You can only look at the graph that interests you. So, if you're a linguist or if you're a syntactician, you can just look at the grammar thing. If you are interested in semantics, you might only look at the semantics or the KR or the lexicography. There's lexicographers might want just to think about what's missing from my dictionary and stuff like that. And if you want to use the distributional approach, you can use it in several different places, right? Instead of connecting to WordNet and Sumo, you could just use your BERT embeddings for the concepts and try to do some learning of the matching process. And we did some of that. And you can make it more distributional, which was what this paper we did in this paper, by extending this semantic framework with this distributional representations. So let me see what I wanted to. Now it's getting hairy because there's lots of complications that we have to do the matching. One thing is to kind of giving a sentence. I want me or my system to produce a system of graphs, and that's hard enough. But once you get the system of graphs, you actually wanted to use these graphs to prove either entailment or contradiction or neutrality. And some of the issues here are exactly how you're going to do some naming technique that will allow you to do this matching, because you need to know which bits you're going to compare to which bits. So if you have something totally trivial like John arrived and John didn't arrive, you have to kind of say, oh, this John goes to this same John, this arrive goes to the same arrive. But was completely, it created a new context, and it's completely, so you have to do this traditional matching and similarity to make it work. And we had to do some experimental work to show that this thing works as well as traditional things. And I don't think I want to kind of go through it, but you can read the paper and you can ask me questions, because the point here is to show how to use the bits that people have annotated to show the things that we want to annotate. to show how well our system does in this case. So I'm going to just skip this and that, which is again about using the context to show, in this case here, the idea was to say that the logic of conjunctions and disjunctions, this is not our work, this is work by Dasgupta et al. In 2018, and they were showing that the NLI sets have difficulties dealing with conjunctions and disjunctions, and so we just use their stuff to show that our stuff does the logic correctly. And but you know, it's just about doing experiments that will convince other linguists that only want to look at numbers. And so we get 99.5 accuracy in the tests, and you're going to say, well, but Valeria, isn't that totally trivial logic? How come you don't get 100%? And we don't get 100% because the whole analysis is based on the parser, on the dependence graph, on the conceptual graph, and the contextual graph. So everything depends on what happened before. And you get the first thing wrong, everything kind of goes wrong as well, to a certain extent, because you do kind of have this ability, you know, we are considering these concepts of ours, so we still have this possibility of getting the symbolic inference to work, even if some of the construction of the semantics is wrong, because the matching happens in a fuzzy way, in a way that is robust. And so I had some preliminary conclusions that this division of semantic labor is beneficial for both the symbolic and the distributional approach, that JKR fulfills its role of strict separation between the conceptual and the contextual structures, and separation of the sentence and information in several different layers. And in 2019, when this paper appeared, because if you remember, I had 5 papers in a slide, and I kind of picked up the one in the middle and said, oh, I'm talking about this one. So in 2019, we had promising results, which were the ones that I just skipped, the ones using the Dasgupta work. But then we carried on, and we actually managed to get it to work properly, and everything could be announced, and Katerina could get her thesis submitted and approved and everything. And then I kind of decided to kind of try to tell you another side of this work, which in some ways is very independent from this one. So far we're talking about generics of thinking about meanings of sentences and checking whether the sentences entail another sentence, whether they contradict another sentence, whether they are neutral to other sentences. But you know, all the work that people have been doing with this gigantic corpora that they have depends on this business of the Turcos marking this inference or not properly, being logical, the Turcos themselves. And this is a little bit dubious, because your Turcos kind of need to get money, and they have to do this very quickly, and they're part of society, they have all the biases that everyone else in society have, and stuff like that. So, you know, lots of the things that the Turcos kind of come up here are very sexist in some ways, you know, kind of women cannot be doctors, you know, the motorcyclist is always a man. So you can see the biases of society showing up in the big corpora. And so separately from this work that I was talking about so far in the 5 papers, we had been doing a different sort of work, which was to check if the natural language inference corpora satisfy kind of logical conditions as we wanted them. So for that we are using this corpus called SIC for sentences involving compositional knowledge, and which is much smaller, which is the reason why we use them. And we kind of started looking at this corpus SIC because in May 2016, Go announced that they had the most accurate parser ever, and we thought, well, okay, if the things are so good, and this corpus is particularly easy, then on this corpus we ought to be able to do logical inference. And I'm afraid, we had 6 papers trying to kind of check whether SIC works the way it should. And we have another one submitted now, but it wasn't very easy, and that's the thing that I actually pestered Sophie in several card journeys, trying to decide why do we have so many problems with inferences that are complicated? The stuff that I indicated at the beginning when we had that last sentence where 3 Turks said neutral, 1 said contradiction, and 1 said entailment. These things actually happen much more than you might expect. And so there's plenty of recent work showing that it's not because the Turks are sleeping or wanting to do things quickly or something like that, but actually there is kind of different, sometimes, interpretations of the sentences that actually are both logical, and if you could ask the person, the Turk, why he decided that was true or false, then you would agree, or that entailed or contradicted, then you might agree with them. But as it is, the systems that we have at the moment are not very competent with that. And so these are the papers, and these are the 2, Katerina as before, but Levy, and these are one of the first things that we discovered is that the way the corpora is all those corpora are organized, you didn't have contradictions being symmetric. And logically speaking, if A contradicts B, then B contradicts A, and there is no way out, right? You can't have things that A contradicts B and B doesn't contradict A. So that was one of the first correcting contradictions. Then we kind of had this issue that everyone knows, every logician knows, that humans are not so good with implications in one direction only. They tend to hope that things are always by implication. And we kind of did several different bits of work for that. So we kind of can ask if the annotations in SIC are logical, can we trust them? And we want to trust whatever corpora we decide to use for these things, right? So we kind of had lots of things that we did to kind of find ways of making the corpora better, including very recently, and you can read some about all the other people working on this problem, all the kind of lovely things that they discovered about how bad these corpora are in general and how non-logical in lots of ways the deep inference systems are. The deep inference systems, lots of times they get hold of things that are not supposed to be the case. So it's very easy to think about that in terms of vision. Like there's a very traditional, there's something that one of the important guys in Stanford kind of always uses as an example. You have all this corpora just trying to say that the deep inference system is better than humans at deciding when something is a wolf, when something is a dog. But actually, when you kind of look at the corpus, all the wolves are in the snow. So the system actually, what it does is to decide when there is snow in the picture or not, and detecting snow is that simple. There's another one that's as good as, which is about tanks, discovering when there's the big machine, the big cars versus tanks. And again, there was a watermark of the Department of Defense that showed that when things were tanks as opposed to. And in the case that I showed before, there was this business of, it's very easy to say that examining the troops is very different from sleeping. But, the system kind of always says that sleeping is going to give you a contradiction. Whether, even if the sentence was, he was snoring, he was sleeping, the system will give you contradiction because it learned falsely that sleeping always gives you contradictions, because in the system, in the most of the examples it does. So final real conclusions here. We do think that this division of semantic label between symbolic and distributional works. We have implemented this JKR with strict separation. We have this concrete proposal for injecting distributivity in JKR that I did not show you because it was a different paper and I don't remember enough of the details of that. We had finally produced a correct SIG, and we submitted a paper on our annotations and Turing provers that show that this new SIG is kind of correct. And we are now trying to harden the system and do further data sets. And our distributional version is BERT, the easy version of BERT. So people might say, well, people do say you should be using Roberta because BERT is not that good. And we have plenty of new ideas, new language, different improvements that we need to do. And the information is here if you want. But I wanted to show you this screenshot that we actually used in our math folder sort of project. So, here we are looking at, because you see, I did talk an awful lot about the symbolic system, but said hardly anything about the deep learning system and how the two are put together. The deep learning system is just BERT out of the box, as it's called easy BERT. So there's nothing much to discuss about it. The symbolic system is difficult, so that's why I spent so much time on it. But how you put the two together is also a slightly complicated thing. And this figure is supposed to show you a little bit more about how this makes the deep learning system more explainable. Because, so the sentences are, Mary believes that John is handsome, and the hypothesis is John is handsome. And you can see that the deep learning system looks at these two things and says, oh, there's an awful lot of lexical overlap, right? Because John is handsome appears in both sentences. And the symbolic system says, yep, there's an awful lot of overlap and there's an equals match here, but there is an averistical context, because it actually knows that just because we believe something does not mean that it's true. And so and this is what I think is kind of rather cute, because you kind of see that the deep learning system says entailment, and the symbolic system says nope, neutral. And you have to put the two together, and you have a little bit of a dial that you can play with and decide in which, if you want to trust more the deep learning system or trust more the symbolic system. And I finally will stop here, but I think we can play with the systems if you guys want, or you can ask questions. Thank you. It's been a tour de force. Go ahead.
I mean, given the importance of the context, both on your end, but also on the human end, who's people interpreting the same sentence differently because of the responders' different contexts. Is there any hope of getting data sets where the person answering whether it's a consequence or a contradiction, that they can say context?
Yes, I mean there's some of the, when I gave you this example here on the, what we did with some of the systems here, about this one explaining natural language inference, was exactly to create a system where you ask the person who is marking to say why they say so, and kind of give a one-line explanation and stuff. It's not very easy to do in real life, because lots of times, and we did that with people who were not in need of money or in a desperate situation in terms of time, because we had some students in the University of Colorado with Professor Marta Palmer there, and so the guys were linguistically experts. Kind of they knew what they were talking about. They didn't have time pressures or anything like that, and it was very surprising to see the explanations that people came up for their answers. So things like, there was a sentence where someone's kind of going to the tennis court, or kind of playing, going to the tennis court, or running running would be kind of sensible. You could run in the tennis court, but something completely unrelated, kind of, eating popcorn or something. And the guys the students kind of, when they reply, instead of saying, okay, these are neutral, they're unrelated, nothing, there's nothing to do with kind of eating popcorn and and playing in the tennis court, they would say, well, but you could, if you could eat popcorn while you are playing tennis, or you could be eating. So people would invent stories, kind of, not because, I don't think they were being, they're not kind of, I think they are not kind of wanting to be nasty. They actually were unclear on what was that the task was trying to achieve. So, kind of, the task looks very easy the way I explained it, right? And people who kind of have more of a background in logical mathematics is kind of used, people like that are used to thinking about, throw away the stuff that's not important, just look at the relevant thing here, does it follow, does it not, and stuff. But people in the middle of the streets don't have that much of a, well, at least I discovered that they didn't. For me, it was a little bit of a surprise that they couldn't just say, oh, come on. So, yeah, kind of, this is important, as you're saying, because, explainability of the black box, that is deep learning, is one of the things that we actually need to have. And I think very recently I saw something about people kind of going back into this idea of trying to break down the end-to-end pipelines that deep learning normally uses now into bits to try to find where things are happening, in particular where things are going wrong. Thank you. Sure.
What do you think about the use case of the temporality of use judgment, right? Like saying a man is sleeping, and saying a man is fixing his house.
Yes.
There's going to be very few probably circumstances in which for example, intelligence is being processed as saying these two things definitely happened at the same time, versus this thing definitely happened at some point, this thing also definitely happened at some point.
Yeah, no, you're right. I mean, temporality is one of the difficulties in natural language understanding. Everyone knows that, and this system, the logical system that I presented, does a very trivial thing about it. It says things like there was something in the past. I mean, it uses Reichenbach kind of view of times, which is a traditional thing for 40 years ago, that there is an event time, a reference time, and this kind of stuff. So it does this very trivial kind of stuff. This is not enough, and I mean, there's kind of for mathematicians in the audience, I mean, there's a very famous example, like, if I smile when I came out, the interview went well. So, it looks grammatically as a future thing, right? I mean, it is future in the sense that if I smile, the interview went well, but the interview hasn't happened yet, even if it says the interview went well. So the stuff that we can do is very limited. And it is one of the things that, okay, let's come clear. The symbolic system that I have, it's very preliminary. I said that it does almost it doesn't even do everything that the bridge system did in 2007. It's just almost everything, but not everything. So, and in the system in 2007 did not solve the problem of natural language understanding, right? There's loads more that needs to be done. Loads. Sure.
So, I'm not super familiar with the literature, but I'm wondering if you can say something about other approaches to solving this contextuality problem. So in particular with an example like John prevented the fight, and say if I wanted to figure out was there a fight, this seems like a problem that you could solve using something like belief revision.
I think the traditional solution is of a friend of mine, maybe friend, a teacher of mine, which is a very famous guy, Jerry Hobbs, who have this, it's called existential promiscuity or something like that. And it is about this business of things that have existence in different slices of time or slices of things. That's the most traditional thing that people used. Notice that it's not about beliefs as such. We're talking about what's happened in the real life as opposed to the beliefs of an agent. So it's not about belief revision, but it's about description of what happened in the universe, in the world itself. And this ontological promiscuity, I think is the name of this theory of Jerry Hobbs, is what people mostly use. Jerry is very famous for temporal ontologies and all the work on what happens when. He's, I think, one of the world authorities on that. And all the work that nowadays we use in the web, because he created this system called TimeML that has been adapted to all sorts of situations on the web, and so when you buy things and stuff like that, everyone uses his formalization of how time should work. And he's a believer on this idea that ontological promiscuity is, I think it's he's making a joke against himself, but it's a good joke. There's too many existential statements and stuff.
So I'll go ahead and stop the recording here, but